Paper 2 from November 23, starting off with defining the term homologous series. We see this term in organic chemistry to refer to a family of hydrocarbon compounds with the same functional group and therefore general formula. So we will start off by answering family of compounds with same functional group as well as general formula. What else can we say about homologous series? Homologous series like alkanes, alkenes, alcohols, they all have similar chemical properties. They undergo the same reaction types, reaction mechanisms. They also have varying physical properties, gradually changing with increasing size, decreasing size, where the differing hydrocarbon units will be CH2. Methanoic acid, Lewis structure can be drawn with the central carbon double bonded to oxygen, which will have 2 lone pairs, and then single bonded to water. In turn, single bonded to oxygen, which in turn is bonded to hydrogen with 2 lone pairs. Finally, the central carbon will be bonded to a hydrogen as well. Only oxygens will have lone pairs, hydrogens, carbon, no lone pair. Moving on to the next question, we are looking at methanoic acid and we're going to find the percentage by mass of oxygen. 2 oxygens in 2 hydrogens. 1 carbon and 2 oxygens. If we do the math, we will get 69.52%. Obviously, provided we multiply the fraction by 100. Comparing methanoic acid with ethanol, which have similar molar masses and therefore similar magnitude, similar size of London dispersion forces. If they have different boiling points, it means intermolecular forces other than London dispersion forces must be different. The reason behind methanoic acid having higher boiling point is methanoic acid has hydrogen bonding. Methanoic acid has hydrogen bonding, while ethanol only has dipole-dipole. And which is stronger? Hydrogen bonding is stronger. Ethanol and methanoic acid are both soluble in water because they are polar molecules. But the question states fully miscible. It's beyond soluble. It's mixing very well, in other words, interacting very well with the solvent water molecules. And that's probably because hydrogen bonding is available definitely between methanoic acids, but also ethanol as well. But did we just not say that ethanol does not have hydrogen bonding, but dipole-dipole only? Well, by definition, hydrogen bonding is what? Electrostatic attraction between the hydrogen bonded to an oxygen and an oxygen. Yes, ethanol cannot have hydrogen bonding with another ethanols because we do not have the OH interaction where H is bonded to an oxygen. But if we had water around ethanol, the hydrogen that interacts with the oxygen of ethanol is bonded to oxygen. Therefore, the interaction between water, solvent water molecules and ethanol, by definition, is hydrogen bonding. hydrogen bonding. Comparing methanoic acid, ethanal, and hydrochloric acid. For electrical conductivity, we want to see how well the compounds dissociate into ions. We know hydrochloric acid will fully dissociate into H+ and chloride ions. Completely dissociates, meaning if we have 1 mole of hydrochloric acid, we'll end up with 1 mole of H+ and 1 mole of Cl-. Therefore, HCl will have the highest electrical conductivity of all, followed by methanoic acid. Why methanoic acid? Weak acid. A weak acid that partially dissociates into H+ and the conjugate base, methanoate ion. With ethanal being the least electrical conducting solution. In fact, ethanal does not dissociate at all. But does that mean that ethanal does not have any electrical conductivity at all? That's not true. There is some electrical conductivity in ethanal solution due to water solvents. Water solvents will dissociate partially into H+ and OH-, which confer ethanal solution some electrical conductivity, but no electrical conductivity due to ethanal itself dissociating. HCl fully dissociates into H+ and Cl-. What are these? These are mobile ions, freely moving mobile ions. CH3, HCOOH partially dissociates into H+ and methanoate. Ethanal, CH3CHO, does not dissociate into any of the mobile ions. Hydrogenation of carbon dioxide can result in formation of methanoic acid. Well, this, if possible, would be a great way to remove carbon dioxide. That's the culprit behind global warming. Carbon dioxide is best known for greenhouse gas that contributes to global warming, and if we can remove by any means, would be a great way to make the environment better. So CO2, greenhouse gas, may be removed to alleviate global warming. Equilibrium constant expression would be Kc equals to product methanoic acid concentration over the reactant concentrations, CO2 concentration multiplied by the hydrogen, H2 concentration. Delta H for hydrogenation of methanoic acid may be deduced by looking at the bond enthalpies of the reactant particles as well as the products. Let's start off with CO2. CO2 has 2 COO bonds, while H2 has 1 H2H single bond. This results in methanoic acid that has 1 COO, 1 carbon to oxygen single bond, 1 oxygen to hydrogen single bond, and finally 1 carbon to hydrogen. All we now have to do is look up the data. We'll go to section 11 and work out how carbon to oxygen double bonds has 804. Kilojoules per mole, but we'll multiply the number by 2 because there will be 2 carbon to oxygen double bonds. Hydrogen to hydrogen single bond is where? Hydrogen to hydrogen is right here, 436. 436, there will be 1. Carbon to oxygen double bond, there will be 1. Carbon to oxygen single, there will be carbon to oxygen single, 358. OH, O2, hydrogen, 463. And carbon to hydrogen. Carbon to hydrogen, 414. Let's sum these up so that we have the equation delta H, that's hydrogenation, delta H, as sum of bonds broken. Now that's the sum of the reactant bond end of piece. Take away the sum of the bonds released. Sorry, bonds formed, not released. Energy will be released from bonds formed. If we do the math, we will end up with bonds broken. Sum of bonds broken will be plus 1240. Take away 1235. That gives us overall only 5 kilojoules per mole. That's unusually small delta H value. Assuming 1% uncertainty for each bond enthalpy. Okay, so bond enthalpies are assumed to have uncertainty, percentage uncertainty values, and that's 0.1%. Determine the resultant percentage uncertainty of the calculated. So we're going to have to find the percentage uncertainty for delta H, and to do that, we're going to have to work out the absolute uncertainties for each bond enthalpies, add them up, and then find the percentage uncertainty. So to do that, what we're going to do is multiply 804 by 0.01. 0.001, which corresponds to 1%. That would be 0.804. 0.436. Again, 0.804. 0.358. 0.463, 0.414. Let's sum all these absolute uncertainties together. That would be 0.804 multiplied by 3 plus 0.436 plus 0.8, we've already taken that into account, 75358 plus 0.463 and 0.414. If we do the sum comes out to be 4.083. Now, the unit is going to be kilojoules per mole. And what we want is the percentage uncertainty that arises from 4.083 out of the delta H we calculated, which is 5 kilojoules per mole. This is quite high. That comes to 81.7%. 81.7% is quite high, and because we are dealing with one significant figure for the percentage uncertainty, we also need to deal with one significant figure so that we will end up with 80%. We have the delta H value of positive plus 5 kilojoules per mole, which is quite small, but still endothermic. Therefore, increase in temperature would result in the system counteracting to decrease the temperature by favoring the endothermic reaction. The endothermic reaction will be forward reaction, and therefore the value of Kc would increase, but only by a small amount, because the extent, the magnitude of the delta H is very small. So Kc would increase. Drawing the energy profile diagram, where we start off with carbon dioxide hydrogen reactants, we'll have to draw our product, methanoic acid, at higher potential energy than the reactants. Why? Because we are dealing with an endothermic reaction where delta H will be a positive value. But of course, the positive value is only 5 kilojoules per mole, so quite a small delta H. So it may be more accurate to actually lower these guys, and it will be more accurate to indicate a very small delta H value. However, there will be yet higher potential energy state of our reactants, and that we call transition state. Transition state. Which will have energy difference with the reactants, which we refer to as the activation energy. And the energy profile diagram is completed by having a curve that joins reactants, transition state, and the methanoic acid product. If we add catalyst, what happens is the activation energy is lowered, is reduced. And that's because catalyst provides an alternate reaction pathway, meaning that we'll have a new activation energy. If we call the activation energy uncatalyzed, we can have another activation energy that's catalyzed, EA catalyzed, which means the transition state has lower potential energy, and therefore we have a lower peaking energy profile diagram. Factors that affect the reaction rate include temperature, concentration. Concentration is for liquid. We can introduce the idea of pressure for gaseous reactants, which applies to our case. We have the gaseous carbon dioxide reacting with hydrogen. Therefore, pressure is a factor that could affect the rate of reaction, not concentration. We would have surface area. Surface area would only apply to solid state reactants, so not applicable in our case. Catalyst, we've already looked at. So besides temperature, pressure is the only factor that would lead to change in reaction rate. And if we want to increase the reaction rate, we need to increase the pressure. How does increasing pressure lead to reaction rate increase? Well, collision frequency needs to increase. Collision frequency can increase by having the reactant molecules more closely packed, more densely packed. Reduce the distance between the reactant particles so that they don't have to travel as much. They need to travel just a little bit for collision. So collision frequency increases. Successful collision frequency will also increase, leading to reaction rate increase. Methanoic acid HCOOH has the electronegative oxygen that takes -2 oxidation state. 2 oxidation states in total -4 that are going to be balanced by 2 hydrogens, 1 plus each, meaning carbon needs to contribute 2 plus oxidation state, plus 2 oxidation state for carbon. Methanoic acid as a carboxylic acid can react with an alcohol to produce ester as well as the byproduct water. This reaction we call condensation because water is being condensed out. The reagent for this reaction, when we have methanoic acid known, will be methanol. The alcohol, methanol. Will be an alcohol, but we know it's going to be a methanol because the ester we're dealing with is a methyl methanoate. We're given that the ester produced is methyl methanoate, meaning methanol and methanoic acid have reacted. The catalyst would be sulfuric acid, H2SO4, and we want to make sure that we use concentrated. Apparently, we're not producing 100% of the ester as we expect. We expect there to be 1-to-1 molar ratio of methanoic acid and the ester. Why is that? It's because HCOOH reacts with CH3OH to produce HCOOCH3. We're dealing with 1-to-1 molar ratio, and that means the amount of HCOH should equal to the amount of our ester, which clearly doesn't, which clearly will be less than the amount of methanoic acid. And we're going to find the percentage yield. How do we find the percentage yield? Percentage yield is going to be the actual over theoretical, expected. Actual being the ester amount, expected being the methanoic acid amount. What's the amount of ester produced? Well, we're given 1.72 grams, the mass of methyl methanoate. All we need is the molar mass. All we need is the molar mass information of methyl methanoate. If we work it out, 4 hydrogens, 2 oxygens, 2 carbons, do the math, we'll be given 60.06 grams per mole value, which will be divided by the amount of methanoic acid, where we're given 2.83. 2.83 grams divided by the molar mass of methanoic acid, 46.03 grams per mole. Let's do the math, and we'll be given 46.5%. That's quite low percentage yield. Both methanoic acid and methyl methanoate are colorless, but we can differentiate between the two by using IR spectroscopy because the readings will be different due to different groups present. Both of them will have carbonyl group. Let's draw the structure of methanoic acid as well as methyl methanoate. Both have carbonyl. And what's the reading for carbonyls? Carbonyl at 1700 to 1750. Don't bother looking up the infrared IR data, you just have to know 3 readings, right? Carbonyl, hydroxyl in alcohols, and hydroxyls in carboxylic acid. Where the carboxylic acid will have the reading of OH group in carboxylic acid will have the reading of 2500 to 3000. In methanoic acid only, absent in methyl methanoate, will give hints to differentiate the 2 reactant and product. NMR data. We unfortunately do not have the NMR data, but we can expect what they will look like. The question is asking us which one the data would refer to. Well, we can get both NMR spectrum to look like. We would expect for methanoic acid 2 signals, 2 peaks. We would also expect 2 peaks for methyl methanoate. But for methyl methanoate, we have more number of hydrogens, which means that the peak intensity will be greater. 2 peaks for both compounds, where one of them will have 1 peak that is 3 times bigger than the other. So we would expect methyl methanoate to have one of the 2 peaks to be 3 times bigger. Of course, we could look at the chemical shift value as well, but the question is not asking us to do so. Methyl ethanoate, methanoate obviously is an ester. Methyl methanoate looks like what? Looks like this, where we can structurally isomerize the structure, where we can move the methyl group to the carboxylic part, so that we end up with a carboxylic acid identity, which would now become an ethanoic acid. How is ethanoic acid produced? Ethanoic acid can be produced from oxidation of alcohols, specifically primary alcohols, not the secondary alcohols, because secondary alcohols will be only oxidized to ketones. Alcohol, ethanol, would be the precursor of carboxylic acid, ethanoic acid. Carbon disulfide is like carbon dioxide, where carbon is double bonded to 2 sulfur atoms, where each sulfur will have 2 lone pairs. So both carbon and sulfurs are happy with full octet. Water can be added to carbon disulfide to produce carbon dioxide and hydrogen sulfide, for which we will calculate the delta H. We're given the delta H formation values for some of the reactant end products. If we have the data for the rest of the reactant end products, we can set up Hess cycle and work out delta H. Let's look up the values for H2O and carbon dioxide. We'll go to data booklet, where we will have data for water and carbon dioxide right here. -285.8 kilojoules per mole, and carbon dioxide 393.5. 393.5 minus delta H equals to sum of delta HF products minus the sum of delta H formation of reactants. Now, for some reason, if you don't remember this formula in the exam, you can work out this formula. How? Set up the third list of constituent elements of the reactant and particles below the equilibrium sign as carbon, solid, sulfur, gas, and sulfur will be existing as solid in standard state. So sulfur solid, and oxygen gas, hydrogen gas. And what we say is, to form carbon disulfide, we would be inputting 88.7 kilojoules per mole. To form water, we will be releasing 285.8 kilojoules per mole, but we're going to have to multiply that number by 2. Why? Because by definition, delta HF is the enthalpy change when 1 mole of water is formed, not 2. Which means if we're dealing with 2 water molecules in the reaction, the delta HF value needs to be multiplied by 2. Carry on to have carbon dioxide as minus 393.5, and finally 2H2S, like water, we'll need to multiply the delta HF value for H2S by 2. Then delta H will be minus 88.2, 88.7, minus bracket minus 285.8 times 2, plus minus 393.5, plus minus 20.6 times 2, which equals to delta H equals sum of delta HF products minus delta HF reactants. I'm going to save myself having to write all these, having to calculate all these values, and I've pre-worked out the value to be overall minus 39.8 kilojoules per mole. We have drawn carbon disulfide molecular geometry beforehand. How? We have carbon double bonded to 2 sulfur atoms in a linear molecular geometry. We call the molecular geometry for carbon disulfide linear because there are 2 electron domains where both electron domains are bonding. Molecular geometry for H2S is going to be single bonded hydrogens, 2 hydrogens, with 2 lone pairs on the sulfur. Now, how many electron domains are there? 4. There are 4, out of which there are 2 bonding pairs and 2 lone pairs. We refer to the electron domain geometry as tetrahedral, but molecular geometry as V-shaped or bent. I did mention just now the reasoning behind the shapes. That's because carbon disulfide has 2 electron domains, while hydrogen sulfide has 4 electron domains, out of which 2 bonding pairs competes with 2 lone pairs. I'd like to talk about how carbon disulfide and hydrogen sulfide are very similar to carbon dioxide and H2O. Why is that? It's because sulfur is an element just below the element oxygen. They both belong to the same group, 16. And what properties do the elements in the same group have? They have similar chemical properties. Just like oxygen bonded to carbon dioxide, to carbon in carbon dioxide, so will sulfur. Just like how oxygen is single bonded to two hydrogen atoms with two lone pairs, so will sulfur. So sulfur has 4 different mass isotopes, and the lowest mass isotope, 32, has by far the highest percentage abundance. Therefore, we would expect the relative atomic mass to have a value close to 32. But specifically working that value out, we would need to do 32 times 0.9 plus 33 times 0.01, corresponding to 1%, and then 34 times 0.04 plus 36 times 0.05. If we do the math, this all comes down to a value of 32.29. The different percentages of different isotopes have been determined by usage of mass spectrometer. Apparently, the 36 mass 36 isotope has percentage abundance that's a lot lower, 0.01%. So if we want to work out the number of sulfur atoms within 1 grams, what we'll need to do is first work out the amount of sulfur in 1 grams, and then take 0.01% of that, multiply by the Avogadro's constant number. So let's start off with the amount of sulfur, natural sulfur, in 1 grams. N equals m over big M, where mass 1.00 grams will be divided by the relative atomic mass of sulfur, 32.07 grams per mole. Then we will multiply this number by 0.001%, which will give us the mole, the amount of mass 36 isotope, and we'll then multiply the number again by 6.02 times 10 to the power of 23, which will give us the value of 1.88 times 10 to power of 18. And the unit now will be atoms. Beryllium chloride is an electrolyte in molten state, where at the cathode and anode we will be having beryllium and chlorine produced respectively. Molten beryllium chloride is going to be an electrolyte for one reason, because contains Be2+ and Cl- ions that are mobile and can move towards, for beryllium 2+, cathode, and Cl- to the anode. Beryllium would be migrating, would be attracted to the cathode, yes. Cathode attracts. Cathode is an electrode that attracts cations by being negatively charged, which means that in the anode we'll have positive electrode attracting the anions, where the anion Cl- would be oxidized to Cl2, releasing electrons. Let's go with 2 chloride ions, liquid state, turning into gaseous chlorine, releasing 2 electrons. We expect the ionization energy to increase across the period generally. From lithium to beryllium, definitely. Why? Because the nuclear charge increases by +1, 1 plus charge. That's because beryllium has one more proton than lithium. However, beryllium also has one more valence electrons. But valence electrons do not contribute to the shielding effect by the inner electrons. The shielding effect is of equal size for both lithium and beryllium, which means that the effective nuclear charge is higher for beryllium. What's effective nuclear charge? Effective nuclear charge is the number of protons minus number of non-valence electrons that are shielding. So the electrostatic attraction between the nucleus and the ionized electron will be stronger for beryllium. Let's write that down. Nuclear charge higher in beryllium, which has equal shielding effect as lithium. Therefore, electrostatic attraction between the nucleus and valence electron stronger. But unfortunately, there's an exception. From beryllium to boron, there is not an increase but decrease. There is a reason for that, and that's because the electron being lost from boron is at a 2p orbital, where beryllium has the electron being lost from 2s orbital. Now, what's the difference between 2s and 2p? 2p is more energetic, is at higher energy than 2s, which means that the electron within that 2p are further away from the nucleus and therefore more easily lost. Let's put that into writing. Boron has ionized electrons, removed from 2p orbital. That is higher in energy than 2s orbital of beryllium. Therefore, less energy required for removal of 2p electron to infinity.